Hey everyone, this is Daniel for Rock the JVM, and you are watching a long-form tutorial on gRPC in Scala with FS2. So in this video, I'm going to show you step-by-step how we can make two microservices communicate via gRPC using HTTP4S, FS2, and CATSeffect. So I recommend that you have at least some basic familiarity with these libraries. I have a bunch of other videos here on the Rock the JVM channel. So to make the most out of this video, I recommend, as always, to write code with me. And whenever you need to refresh your memory, just refer back to this video or to the written form at the blog with the link in the description. The blog also has all the files, all the code, and all the explanations and instructions that you need. Okay, so without further ado, I'm going to navigate back to my little IntelliJ project that I made specifically for this video. I have a little object called gRPC demo. This is an I/O application from CATSeffect, so I'm importing CATSeffect here. Now, this project is a little bit different than other demonstrations that I've made here on the Rock the JVM channel because this project contains two small projects. One is called Protobuf because gRPC requires the presence of some protocol buffer files. So we're going to describe the data structures in special files called Protobuf. So I created this Protobuf project here with a bunch of Scala libraries that will compile proto files into Scala case classes. I'm going to show you that in a moment. And the root folder, which contains HTTP4S, some FS2, and some CATSeffect libraries. Obviously, they will be imported as dependencies. This build.sbt file you can find in the blog post, which I recommend that you keep handy. Now, besides the build.sbt file, you will need a plugin that will allow SBT to compile proto files into Scala case classes, and you can find this under the project, or you can add it to your project subdirectory of your SBT project. It's called plugins.sbt, and this line is very important. SBT FS2 gRPC. This little SBT plugin will allow the creation of Scala case classes from proto files. So make sure you add the build.sbt as well as the plugin SBT files from the blog post into your project before we continue. So you can pause the video to do that if you want. Okay. Now, the first thing that I'm going to do is simulate let's call this order fulfillment for an online store. So this is going to be the use case that we're going to simulate in this video. Now, in the Protobuf directory, or the Protobuf sub-project here, we have source main Protobuf. This is going to be very important, like source main Scala in the big root project. And under source main Protobuf, I'm going to add some files that will describe the data structures that we will use to interact with our services. So I'm going to create a new file here under Protobuf. I'm going to call this orders.proto. The extension is important, and this proto file will describe some data structures with the syntax of Google protocol buffers. So I'm going to have my syntax as proto3. This is going to be the syntax that we're going to use here, and we need a semicolon because that's what the syntax of Protobuf is. Now, I'm going to create a package here, so I'm going to declare it a package. I'm going to call this com rock the JVM protos with the semicolon, like Java, because protocol buffers were created initially for the Java libraries at Google. And we're going to describe a case class, and this is called a message in protocol buffers. So I'm going to have message. I'm going to call this item. And this item thing will have some fields. We'll have a string name equals 1. This means that the name field is called name and occurs the first in the data structure. So notice the syntax here, string with lowercase s, message, and so on and so forth. So string name equals 1. Let's call an integer. So an int 32, that's the type. I'm going to call this quantity equals 2. This is going to be the second field. And double amount is equal to 3. Amount means the price, or the total amount of this particular item order. So you order items in packs. Maybe you want to order 2 iPhones. So you have an item data structure with name equals iPhone, quantities equal to 2, and amount is equal to maybe $15,000 or something, whatever you pay for 2 iPhones these days. So this is going to be the data structure. So message item with this sort of syntax. By the way, if you want the syntax highlighting that I have here in IntelliJ, you can install a plugin for protocol buffers in IntelliJ. By default, IntelliJ doesn't support this sort of file, so you'll see them as plain text. Okay, so this is going to be our data structure. Let's define some more. So I'm going to have a message. Let's call this order request. made of multiple items. So I'm going to have an order request of an int 32. Let's call this order ID equals 1. And let's say we want multiple items. The way that you mention an item array is to say repeated items equals 2. This is going to be an order request with items as a list of item or an array of items. Okay, let's also have a message order reply. So we want to ask a microservice for an order request, and that microservice replies back to us with an order reply. It only makes sense. So we have an int 32, let's call this order ID equals 1, repeated items equals 2, and also let's call a double total equal 3. This is going to be the total amount of this particular order. So we want an order request for a bunch of items. The microservice in question replies back with an order reply saying, hey, I've just dispatched your order and the total amount is equal to whatever, $15,000 or something like that. And that will be reported back to my user. Now, the interface for this interaction will be in the form of a service. I'm going to call this order or order service. And the method there is going to be an RPC. So this is going to be the keyword there. I'm going to call send order stream. That takes an argument in the form of a stream. So this is going to be a gRPC. I'm going to call this order request. So a stream of order requests and returns stream of order reply. And I'm going to add some curly braces here because we don't really have any sort of extra data in this interface. So we essentially define a method called sendOrderStream that takes an order request as an argument and returns a stream of order reply as a response. This is going to be the interface that we're going to use to interact with our microservice that deals with orders. Now, the next thing that we need to do is to transform all of these into Scala code, into Scala case classes, and into a trait that we are going to implement. So I'm going to open up a small terminal here, and I'm going to start my SBT console. And this SBT console will navigate to the Protobuf mini project, and it will ask for a compile. So I'm going to say project Protobuf. I'm going to navigate there, and I'm going to say compile. So notice that we have compiling 1 Protobuf files, 2, and there's a big path here. We have target Scala 331 source managed. This is going to be very interesting. So under target here, we have under Scala 331, this is the Scala version that we're using here, source managed, and we have main, and we have ScalaPB, Rock the JVM, protos, orders. This is going to be the package that we will import in the other project. So this contains the data structures. So notice that we have the case class item, we have all the fields here, order gRPC, order reply, order request, and so on and so forth. So we have all the necessary data structures generated for us that we can import from the other project, the root project. Now, the package that we need to import in order to access these data structures is this one, Rock the JVM, protos, orders. This is what we're going to do. So under source main Scala, in my gRPC demo, I'm going to import everything in that package. So I'm going to import Rock the JVM. We have protos, orders, and star. And if I want to create a small case class, let's call this item, I should have access to the item data structure. So we have item with the name iPhone. We have quantity 1 and price $2,000 or something like that. The 2,000 is a double, if I remember. So that's going to be a 2,000.0. All right, so because the code compiles, now I should feel free to write the rest of my code. So let me simulate the class. Let's call this order service. And this extends order. And notice that we have the ordered and ordering from the Scala packages. And we have a very interesting trait called order FS2 gRPC. This is the trait that we generated from Rock the JVM protos orders. So order FS2 gRPC. And the types that we need to add there is an effect system, so IO, and the type metadata. Metadata from IO gRPC. So I'm going to import IO gRPC everything. I'm going to place it at the top. And I'm going to move the little comment in there. And my order service needs to override send order stream. And this is the function signature that was generated from the proto file. Send order stream. Request is an FS2 stream of IO and order request and returns an FS2 stream of order reply. So let me import FS2 everything. So import FS2 stream. So we have a stream of IO order request and context metadata, and this returns a stream of IO and order reply. This is it. So let's actually process this stream. So this is the business logic, so to speak. So this is business logic of the server or the service. And I'm going to say request, map, and given an order request, I'm going to return an order reply with the same ID. So orderrec.id. So order ID, that's what the field says. Then we have the order request.items. And then we have the total, which is just a reduction of all the items total. So I'm going to have my order request items, map, let's say underscore amount. This is the amount of the little pack of items. And then I'm going to say reduce with underscore plus underscore. So we're going to compute a sum. Let's actually reduce that to a sum. All right. So for every order request, I give back an order reply. This is simple enough. Now, this order service needs to be exposed through a gRPC port as an HTTP port. So I'm going to create an object. Let's call this server. And the thing that I want to expose in this server is a kind of resource of IO and a server that I can actually start on a port. So I'm going to say val, let's call this gRPC server. And I'm going to use the following construct. This order FS2 gRPC is not only a trait, but it also has a companion object. So notice that we have an order FS2 gRPC generated object, and there's an make client, service binding, and so on and so forth. And there is a function that has a little method, make client, client resource, stub resource, and there's one that's called bind service resource. So there are a bunch of methods that you can use here. The one that I want to use is called bind service resource, and the service here is the actual class that I had earlier. So I'm going to say bind service resource. Let me get back to my code. So I'm going to say order fs2 grpc.bind service resource, and I'm going to instantiate my business logic by saying new order service there. So new order service there. And this is going to be a resource of IO and server service definition. This is an internal trait from the library. Now I'm going to flat map that, and I'm going to create an actual Netty server. So I'm going to have a flat map. And given the service, I'm going to say Netty server builder that I need to import. So Netty server builder is from IO gRPC Netty whatever. I'm going to say Netty server builder for port. I'm going to use 9999, and then I'm going to say add service. And notice that we have a server service definition. I'm going to add my little service. And then I'm going to say this Netty server builder for port add service is at this moment a Java API, but FS2 has some extension methods on top of this sort of construct. So I'm going to say resource IO. And this little extension method needs to be added as an import. So I'm going to say import FS2 gRPC syntax all. And I'm going to add a star there. And notice that the resource now became blue. So this is an extension method from a server builder ops, and there is a conversion from my server builder, which is my Netty server builder, into this server builder ops with all these methods. So let me get back to my code. And now we have a resource of IO and server. And now we can actually use that when we instantiate this in our main application. So we currently have this our gRPC server, let's call this server resource. And we can start it whenever we want, all right? So in my gRPC demo, if I wanted to start the server, I could say something like server, and I think I'm colliding my names here. Let's call this order server. So I'm going to say my order server dot gRPC server resource, and then I can say use, and I can actually start that. So I can say use with IO never. All right, so I could actually allocate a port and start this as a gRPC server. Okay, but right now I'm going to keep that to IO unit because I also want to start an actual HTTP server that will accept requests from my user-facing application, and that in the backend will ask the order server, which is the order server, let's call this microservice or something like that. It will ask it for a reply, okay? So let me go set this up as an actual IO application. So this extends io_app.simple. And I'm going to override my run method. So override run as gRPC server resource use, and given my service, I am going to say IO println. So IO println. Let's call this order fulfillment microservice started. And then I'm going to say IO never, because I want the server to be alive. So the service doesn't actually do anything. So as I'm running this little application, this order server will simply print me order fulfillment microservice started. And this is now ready to accept requests at port 9999. But obviously I need a client to do that, which is going to be the next step of my application. So let me start a client. So object client. And I'm going to have a val resource here as well. So I'm going to have my val, let's call this resource. And I'm going to follow a very similar pattern, netty server builder for address. And I'm not going to use netty server builder, but a netty so-called channel builder. So I'm going to say netty channel builder. So I'm going to import that from io_gRPC netty. Let me import everything because I want to simplify my imports. So netty channel builder that for address, I'm going to have localhost, and I'm going to use 9999. I'm going to say use plain text. This is the internal protocol there, and I'm going to say resource of type IO. This is again an extension method from FS2 gRPC. So this is going to be my resource. And using that resource, notice that I'm getting a managed channel. From this managed channel, I need to somehow stub an order service, which is an order FS2 gRPC with this little method that I can call remotely. So I'm going to flat map this resource. So I'm going to say flat map. And using the channel, I'm going to say order FS2 gRPC dot, and there is a function called stub resource, and I'm going to have stub resource with this channel, and this expression will now be a resource which, when evaluated, will produce an order FS2 gRPC instance. This order FS2 gRPC is going to be a stub in the RPC framework. So in the RPC framework, one is a server which produces an instance of the trait. So let's have a trait service with some method definition. The server will actually provide an instance of that trait and open a port to interact. And then the client will return a stub instance of that trait, and whose implementation will interact remotely with the server. So what I have access to is a stub instance of this trait, and from my side, whatever my side is, so from my side, I can just use the stub instance. So I can call the method, some method, remotely. This is the remote procedure call framework in general. So when I invoke the sum method remotely from my side, the stub implementation will actually invoke the server remotely over gRPC and so on and so forth. It will provide a response, and then that response will be fed back to me. So I'm simply calling this sum method remotely from the client side as if I was local on the service side. So this is the general RPC framework. In gRPC, that is Google RPC, we use this sort of framework with FS2 and protocol buffers to implement the nitty-gritty details. But from my client side, I should be able to call the sum method remotely. My sum method in this case is my send order stream, which I can call from the client side by evaluating this resource, because when I evaluate this resource, I'm going to get a stub implementation of order FS2 gRPC. And when I do, I should be able to call this send order stream. Let me give you an example. So in this client, I'm going to extend. Actually, you know what? In the gRPC demo, I'm going to do that. So in my run method, I am going to say client resource. And then I'm going to say use. And using the stub there, the stub or the order service, I can say order service dot, and there's the function send order stream that I can call from my side, assuming that the order service, the order server itself, sits on another application. So I'm going to say send order stream, let's say with stream dot eval, and I'm going to simply put an IO of, and I need an order request. So an order request is a case class. Let's say an order request with ID 0. Then we have a list with, let's say, item. So that's going to be my case class as well. Item, we have the name iPhone, quantity 2, and amount $2,000 or $20,000 because we want some golden iPhones there. And the order request itself will have order ID items, and that's going to be it. Okay, and what I should be able to get back is going to be an order reply. So I'm going to print it out because this order service send order stream is now an IO. So let's call this RPC call. So this RPC call is going to be a stream of IO and order reply. So I need to say compile to list. And this RPC call is going to be an IO of list order reply. So I'm going to flat map that. So flat map. And replies, actually, I'm going to have, say, IO println. And I'm going to say replies dot. Now, as a matter of fact, I don't really need any dots, I think, because the replies is already the list of order reply. Let me check my types here. So an item has a name, quantity, and amount double, and I have an amount string here, so that's not going to be great. So let me actually start my server now. So the order server. So we have an application to work with and have a compiling error. And for some reason, my Scala plugin just throws some dotty errors, actually. So I'm going to resort to my SBT. So let's do a compile here. All right, so we have order service, missing argument, context of method. Okay, and I need metadata here. So I'm going to say send order stream, order request, and new metadata. That's going to be it. All right. I have a different compiling error now. So we have flat map, replies, and so on and so forth. IO print line. We need a cats effect IO unit, which means that I need this RPC call. So RPC call. So let me save that. Let's see. We have another one. And I think it's because of parentheses, actually. This metadata needs to sit outside of my stream. So send order stream needs to have my stream.eval, and then the new metadata as the second argument. Okay, now we have a success. So let's actually start the server now. All right, so the order fulfillment microservice started, and from my gRPC demo app, I should be able to invoke the send order stream and get back some reply. So let's run this. And we should be seeing some case class. We have an exception instead, so we have connection refused. And that would be very weird, because that sort of exception happens if I try to connect to an unbound port. So if I try to run the client again with a different port like 9998, which is almost for sure not going to be allocated, I'm going to get the same exception, connection refused, which means that my order server didn't actually allocate my port. I can check that. So I can go create another terminal here. I'm on a Mac, so I can do, I think it's ls off -I TCP -9999. So no port allocated, which is very weird. Let's go to the server. So when I run this, I say use, and given the server, I have an IO print line and IO never. But of course, I'm stupid because I need to actually start the server. So I'm going to say IO server start, and then do an IO never. So let me rerun my order server. So now we have the same kind of output. Let's check for port. So let me get back to ls off, and lo and behold, we have a process here. So my port wasn't actually allocated because I was stupid enough not to start my server. So let's go run my gRPC demo, and we should see a case class being printed to the console. Okay, that's a different thing. Connection refused. I'm again stupid because I didn't change my actual port, so 9999. Let's run my gRPC demo one more time. And no more exceptions. So notice that we have a list with order reply and so on and so forth. So now we have an actual reply from a server. So from a different application, we could invoke the send order stream that is actually being implemented as an interaction with a remote server. So this is how gRPC works in practice, folks. If you want to wrap this gRPC demo in an actual HTTP server with a front-facing application, with an HTML page and so on and so forth, you can invoke this order service yourself manually by calling the send order stream from your backend application. So this is the so-called backend. The blog post, by the way, has an example of something like this with an index.html with a front page that you can actually invoke with an HTTP server built with HTTP4S. So you can wrap this with HTTP4S and use this as a client to the other application. So there you have it, folks, a demonstration of gRPC in Scala with FS2. I hope you liked this video. If you did, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this. Check out the blog post because it has lots of explanations and some actual demonstration of how this would work with a front-facing application with a web page. And check out my Rock the JVM channel and the Rock the JVM website for everything in the Scala ecosystem and Kotlin and so much more. So until next time, folks, this is Daniel signing off.